let's start off with question 1, yeah? Let me grab a different color, purple perhaps. Let's put it over here. Right. So it says a closed system undergoes a thermodynamic cycle consisting of two processes. Okay. What do you understand regarding a thermodynamic cycle? Okay. In a cycle, right, it goes from process 1 to 2 and then 2 back to 1. That is called a cycle, yeah? Okay, can someone tell me what is the properties, yeah? For the cycle, if we refer to our first law, what is delta U going to be in a cycle? What is the property of a cycle, yeah? Can someone tell me? What happens to your change in internal energy in a cycle? Okay, Ho Jia Hui, what do you think? In a cycle, what happens to the change in internal energy?
Yes, doctor.
Yeah, what happened to the change in internal energy when you have a cycle?
Increase or decrease?
Increase or decrease, correct? Okay, but any more attempt? Someone would like to attempt to complement the answer. Apa ni? Azril. Okay, Azril, would you like to guess? Your friend answered increase and decrease. Okay, almost there. What you think, Azril?
Yes, doctor.
Yes, what happens to the change in internal energy in a cycle?
The change internal energy is 0.
Okay, correct, eh? So both of you are correct, yeah? So one increase and then decrease. Okay, the internal energy goes back to the initial state lah. Okay, so basically plus and minus those two values, you will get 0, yeah? So this becomes 0. Now the first process, okay, 1 to 2, we see 1 to 2. We have 30 kilojoules of heat. So Q1 to 2, you have 30 kilojoules. Okay, during the first process, 30 kilojoules of heat is supplied to the system, while the system is doing work of 50 kilojoules. So, if system is doing work, what do you think? Is it positive or negative? System is doing work of 50 kilojoules. So, it's positive. Okay, so it's 50 kilojoules, yeah? So, the system is doing work. Okay, the system receives heat, it gets excited, and it does work. So, it's positive, eh? Heat is positive, work is positive. All right, great. Now we have a cycle, okay? The next process, the second one is from 2 to 1, okay? We have 35 kilojoules, okay, of work. And then they ask us, what is the heat transfer, okay? Heat transfer is basically Q, yeah? So Q from 2 to 1 during the second process is how much? What you can do now is write down your first law. I'm going to replace this with a different color. Yeah? So 0, okay, equals. So this is your net heat transfer. And this is your net work, okay? So what do you understand by net? Okay, it's not net that you use to chase butterflies and catch butterflies, eh? Not that kind of net. Okay, you know, when we are little kids, we used to fetch our parents' nets, and we used to catch insects, butterflies. Or is it just me? I don't know. So that was me, at least during my days when I was a kid. Okay, but not that kind of net, not mosquito net. This net is actually the total, total lah. Okay, So when we say net heat transfer or net work, we mean the total heat. Okay, the net heat is actually the total heat. Now we say that Q1 to 2 plus Q2 back to 1, right? Then we subtract that with the work from 1 to 2. Let me just delete this unnecessary stuff. Okay, so when we say net, that means work from 2 to 1 also. Okay, so now it's easy. Yeah, it's easy stuff. You can just plug and play, right? So 0 equals what? 30 plus, okay, 30, we are making use the information here, and then plus Q2 to 1 minus work from 1 to 2 is this guy. All right. And then you add up with 2 to 1, 35 kilojoules. Is that right, what I am doing here? I think work from 2 to 1. Okay, can you guys identify the sign of the second work here? 35 kilojoules of work done on the system. What do you think? Is it going to be positive or negative? Q in, heat you supply is positive. Heat out is negative. Okay, so heat in, the pair and the correct pair is work out, right? Okay, and Q out, the correct pair is work in. It's basically the opposite of the top one. Okay, just remember the top one. Yeah, supply heat, molecules get excited and they do work. So work is done to the boundaries of the system. They push the piston, right? So work is out. Okay, so here 35 kilojoules of work done on the system. Okay, that means the work is done, is coming in. The system is subjected to work from outside. So this is going to be a negative 35, yeah? Now, if I just come back to here, right? So this is negative 35. Okay. Solve for the heat transfer in the second process. Okay, I'll give you 20 seconds and I'm just gonna call out a name randomly. Okay, to mention the answer. Okay, let's have Sharifah. Sharifah here. What's the answer? Just plug and play into your calculator. Yeah.
The answer is negative 15.
Negative 15, correct, yeah? Excellent. So the answer is negative 15 kilojoules. Any questions? Yeah, I think this is very straightforward. This is just, let's say, a manipulation of the first law. Yeah. Okay, make sure you have your signs correct. Identify what are the process. Is it work done to the system, work done by the by the system, heat into the system, or heat out of the system? Make sure you understand that and put the symbols accordingly. Okay. All right, the network. Okay, question B. Not internet network, it's net total work. Yeah, net work. That means everything over here. Okay, so W subnet equals W1 to 2 plus W2 to 1. Anyone? Yeah, I heard an answer. What's that? Okay, then I'm just gonna pick let's say Marsha. Marsha, you there?
Yes, doctor.
Okay, this one is very easy, Marsha. Go ahead. Come
50
on.
minus 35, right?
Yes, that's very
Uh,
easy.
15.
15, okay? So that is going to be 15 kilojoule. Very easy. The net work, eh? Okay, then we have C, the amount of heat transfer. We have done B, the amount of heat transfer. Okay, Q net. All right, can I have Faiza?
Yes, doctor.
Yeah, so what do you
Um,
think? How much is the net heat?
kg.
15 kilojoules. All right, good. This one is conceptual, very straightforward. Any questions? Someone then asked me, why plus? Why not minus? Well, it's net, yeah, it's net, which is total. You add up, okay, 1 to 2, process 1 to 2, and process 2 to 1. But you are aware in the back of your mind that from 1 to 2, you have a positive heat supply. From 2 to 1, you have a negative heat, which is heat going out of the system. So if you add a negative, similar to what you imagine Q1 to 2 minus Q2 to 1. Okay? All right. There's no question. Then I go with question 2. A closed container. Ini typo ni. If you have a closed, it should be one container lah. Grammatically wrong, Okay, a closed container insulated with 0.5 kilogram of nitrogen gas. Okay, y'all, tell me, can we use ideal gas for this question? How many say yes? Please raise your hands. Okay, Loh said yes. Zainab said yes. Who else says yes? Okay, Azril. Confident lah sikit. Okay. You're eating. Okay. Okay lah, the rest follow the crowd lah kan. Okay, good, good. Okay, so you can say this is an ideal gas, as I said earlier, yeah, in yesterday's class. If you have gas like air, nitrogen, hydrogen, yeah, like really gas material, yeah. Not like water. Water can be in fluid, liquid, yeah. Sometimes it is in gas form when it is in a superheated vapor state. But nitrogen, oxygen, air, hydrogen, you can treat it as an ideal gas. Okay. Now, let's see. I don't have too much space here. Perhaps I can just put this somewhere. Cut and put it at the bottom. Okay, this is for question 1, yeah? Question 1's answer. So for question 2, this can be treated as an ideal gas. So there's a closed container. 1, 2, 3, 4. Okay, 4 sides of the container's wall. You have a mass of 0.5 kilo. You have nitrogen gas. And then you have the specific heat. CV is 0.7748 kilojoules per kilogram Kelvin. Temperature is at 20 degrees Celsius. As always, when you deal with ideal gas, you have to convert your temperature to Kelvin, right? So you add with 273, you get 293 Kelvin. Then what? Then it has an electrical heater, okay? Let me just draw an electrical heater. Okay, like that. So we know with electrical heater, they will impose work on the system, right? So there's work on the electrical heater, right? W sub elect. All right. Okay, we have the power of the heater is 2.5 kilowatts. Okay, we have 2.5 kilowatt, which is 2.5 kilojoules per second. What is joules per second? We have the heater operating at 20 seconds. So can you guys find out what the work, the electrical work is? You just multiply by 20 seconds, okay? So 2.5 kilojoules per second or kilowatt times 20 seconds, we will get the electrical work to be 50 second goes with second, and then we have kilojoules left. But guys, tell me, is this a positive work or a negative work?
Negative.
Negative, okay, good. Why negative? Because the work is done to the system, yeah? So we put a negative sign here. Okay, what else? We have processed this information, okay? Causes, okay, this electric heater with this power and this much of seconds causes a change in the system boundary, okay? If you draw the system boundary, the question tells us that the boundary has now changed, right? The boundary has changed. So that means it's not a rigid container, it's just a closed container, sort of like a piston cylinder system, whereby the system has now changed boundary, okay? Okay, the piston has moved, yeah? So what can we say about the boundary? Does it do work? It's pushing the system up. It's pushing the piston up. Okay, of course it's doing work, right? It's pushing the piston upward. Okay, so if it's doing work, is it positive or negative work? So we have two kinds of work here: electrical work and boundary work. Is it positive or negative, guys?
Positive.
Positive, yeah, very good. So boundary work, if you recall, is pressure times difference in volume, okay? So we have defined the work, all right? Determine the work done by the nitrogen gas. Now it's time to write our first law, okay? Our first law, I really want to go with the pink color. Okay, first law, change in internal energy equals Q, the heat, the total heat, minus total work done into by the system. Okay. Now, remember that for ideal gas, okay, our delta U can be approximated by one equation. Remember what the equation was? Okay, for ideal gas, U2 minus U1 equals the specific heat times T2 minus T1. Okay, so please refer to the notes from your previous lectures. Yeah, this is the formula that relates internal energy and temperature in the ideal gas law. Okay, so now if you have capital U, you have to multiply your small u with the mass, right? Okay, so if you multiply mass on the left-hand side, then of course you have to multiply mass on the right-hand side, okay? You got it? So left-hand side of the first law is taken care of, okay? You are given already, okay, the information on the mass, the specific heat, second state temperature, and first state temperature. Okay. What was the second state temperature? Was it given? 40 degrees Celsius, right? 40 degrees Celsius. Okay, so we have mass here is still 0.5 kilogram. CV is 0.7748. But temperature now is 40 degrees Celsius. Okay, and the boundary has moved. Okay, this is 273. I think it's 313. We can solve for M times CV times T2 minus T1, right? Okay, so let's just put in, I'm sorry, I'm supposed to use the pink one. Okay, 0. Come on. That one, okay? 0.5 kilograms times 0.7748 kilojoules per kilogram Kelvin times T2 minus T1, which is, it doesn't matter for now because if you do Celsius 40 minus 20 or you do 313 minus 293, okay, regardless of the unit, you will still get the same value. Yeah. So for now, let's put it as K, although we know it's Celsius down here, but you have the same value of 20 if you perform the calculations in Kelvin. Okay, so we say it's Kelvin here, the unit. So Kelvin goes away with Kelvin. What's the output here? What's the outcome here? It is supposed to be 7.748, right? So 40 minus 20 is 20. 20 times half is 10. 10 times 0.7748 is just 7.748. Okay. Kilogram goes away with kilogram. So this is kilojoules. Okay. Delta U. Okay, guys. We are just halfway. Okay. How about Q? Is there any heat supply? Anyone? Any heat supply? Any heat addition? Yes, Zainab is, what does that mean, Zainab? Is there any heat supply or no?
Yes.
Okay, what do you think? Where's the heat supply? Is there any fire or, heat supply? So I think in this question, there is no heat supply, right? We say that Q is 0. Okay. And now we are left with, okay, delta U equals negative. So W is what? W is a combination of electrical work and boundary work, right? So we have W electric plus W boundary. What will we ask for? We will ask for the work done by the nitrogen gas to the boundary of the system. Okay, so it's boundary work. So boundary work is this guy, right? And we say if we want to have boundary work as our answer, then we will have to take this electrical work to the left. Okay. So what would that be? Delta U plus electrical work equals negative boundary work. Can we solve for boundary work? Of course we can, right? So this one is already 7.748. And this one is minus 50, right? From here. Okay, electrical work is minus 50 kilojoules. Uh-oh. It has gone through the boundary of Q1. Wait a second. So then we will have our boundary work. All right. Someone has the answer? What is the boundary work? Hello?
0.252.
42 point? kilojoules. All right. So it's a positive work. It makes sense, right? Because boundary work does work. Yeah, it does work. The system is doing work, right? So the system is pushing the piston upward. So it's doing positive work. Okay. You don't need to calculate the P times V2 minus V1. Okay. Rather, you just use the first law of thermodynamics to find out the boundary work. Okay, I want this one to be sort of a guided one, rather than me spilling the tea to you, telling you all the answers. Yeah. Okay. So why don't we first draw what this question is all about? Okay, we have 10 kilogram of air in the piston cylinder system heated from 25 degrees Celsius to 77 degrees Celsius using an electrical heater. Okay. First of all, can you use ideal gas? What do you think? Ideal gas? Okay. Afika Farhas is agreeing with me. It's ideal gas. Anyone? Anyone disagree? I don't agree. This is not ideal gas. Okay, Azriel also agree. Agree or disagree, Azriel? Which one? Okay, I think everyone with thumbs up is agreeing with me. It's an ideal gas, okay? All right, ideal gas. Now, the more the reason to use ideal gas is because you have the information of the specific gas constant, okay? R is 0.287, and so you know it is ideal gas already, okay? Now let's draw our system. Piston cylinder system. Oh, that's very dark there. You have an electrical heater. What else? You have a mass of 10 kilos. You have a temperature of 25. So with ideal gas, it's always converted to Kelvin. And then you have the pressure is 2 bar, which is 200 kilopascals, right? So this is a state of the gas, and then it undergoes a process, right? So it turns out that during the process, 5 kilojoules of heat were dissipated. Okay, 5 kilojoules of heat is lost to the surrounding. We say that this is state 1, and then we have state 2. Okay, let me just draw a copy, let's say. Copy and paste. All right, but this time around with a different setup. Yeah, we don't have this loss of heat. And then our temperature has now become 77 degrees Celsius. Okay, so that means our temperature at state 2 is different from state 1. 77, that would turn out to be 350 kelvins. Pressure is retained at 2 bars, so 200 kilopascals all the way. Okay, and additional information is CV is 0.718, all right? CV, specific heat at constant volume. CV is 0.718 kilojoules per kilogram K. It's supposed to be kilogram K like that. Okay, when you see CV, you automatically know that you can apply U, small u2 minus u1. Okay, small u2 minus small u1 equals CV times T2 minus T1. So then you can multiply mass with your internal energy, and then you multiply mass with the right-hand side terms, all right? I mean, it looks so ugly, right? So let me just change it to a nicer color. Green. Okay. So now what you need to do is employ the first law, right? But before you even get to the first law, there are a few things you need to do. Yeah. You want to find the electricity supplied, right? You want to find the work, the electrical work supplied to the system. Okay. So work is only one part of the first law, right? So you have delta U equals Q minus W. Okay. And let's say this W is comprised of electrical work and boundary work. So the heat now is actually comprised of heat loss, right? But let's say we have Q in plus Q out, right? There's no Q in, okay, so we can say that is 0. How much Q out? We have 5, but what do you think? Plus 5 or minus 5? Come on, guys. 5:26 in the afternoon. Everyone is sleepy, perhaps. All right, so Zainab and Lo thinks it's minus 5, only 2. So sad lah, I ajar you. Guys, it is actually minus 5, okay? So it's minus 5 because the work is not work. The heat is rejected from the system, okay? Heat in is positive, heat out is negative. All right. Okay, and we know the boundary work. Okay, I want you to solve for the boundary work. Remember, boundary work is pressure times volume at the second state minus volume at the first state. Okay, so this is a constant pressure process. So you don't need to do P2V2 minus P1V1. The P is the same throughout. So you can use the single P value. Okay. So I want you to solve, okay, for first one is delta U. Okay, I will call for 2 volunteers, and then I want you to solve for the boundary work, okay? In the meantime, let me draw the boundary so that you have an idea that you are calculating the work done by the boundary, okay? The gases are excited. The gases in the boundary are excited. Yeah, they jump here and there. They hit the walls of the piston, cylinder system, and the piston moves up. So the piston is subjected to work by the system, by the boundary. So the boundary is doing work. To solve the boundary work, right, you need volumes, right? Okay. So with ideal gas, it's very easy. Okay, use what? PV equals MRT. Okay, so it depends if state 1, P1V1 and T1. If state 2, it's P2V2 and T2, right? So then another 2 volunteers to tell me what are the values of V1 and V2. These two first. Okay, let me put the correct unit there. Get ready, 2%. I will call at random for volume 1 and volume 2. Okay, make sure you use the PV equals MRT. Let's see. Okay. Can I have Ilyani? Yani, are you there?
Yes, Doctor.
Okay, all right. Jangan malu-malu. Don't be shy. It's okay. Tell us what is the volume at state 1.
Tengah kira kejap.
Okay, all right. Okay, I'll keep Ilyani first to the side. How about volume 2? Volume 2. Let me have Haikal. Haikal, are you there? Haikal ada ya. How much is the volume, Haikal? at state 2? You still calculating? Sorry? I think I cannot capture the audio. Does the others, the rest of you capture the audio? We cannot really hear you. I think maybe there's some
Doktor dah.
connect. Okay. What is it? V1.
123.87.
123.87. I think that is not correct. Okay, so P1 is what? P1 is how much? 200, right? 200 kilopascals. And then mass is 10 kilograms, right? R is point what? Where's the information? 0.287 here. 0.287. T is 298. Okay, recalculate Liani and let us know what is the value for V1.
4.276.
This one is correct. Okay.
Sorry.
4.276. Okay. Haikal, are you there? Are you still with us, Haikal? 210 and 0.287. This guy is 350. I think Haikal's microphone is our audio is a bit some issues and technical issues. Can I ask for another volunteer? How about Owen?
Doctor.
Yeah.
Yeah.
Okay, yes.
I'm using laptop.
Okay.
The answer should be 0 to 3.
Great. All right. Thank you, Haikal. So then comes the delta U. Okay. With these two, you can already calculate the work by the boundary. Okay. But now for delta U. Okay, who wants to volunteer? What is delta U? This is delta U. This guy. And this guy also lah. Same thing. Okay. Who wants to volunteer? Make this process quick. Can I have Afifi? Afifi, you there?
Yes.
Can I have the answer for delta U, which is mass times specific heat times the temperature difference?
I think it's 373.4.
373.36 or 0.4. Okay, that's good. Thank you, Afifi. Great. All right, thank you. And then we have the boundary work, which is basically P times V2 minus V1. All right. So someone let me have, okay, the first person here, Alia. Ni semua memang heart attack ni I panggil. Okay, Alia, how much is it? The work done by the boundary. This one. I'm asking you to calculate this one that I'm circling here.
149.24.
Right, correct. Yeah, 149.24. Okay. Great. So everything is in place now. So you just plug and chug, right? So let's say the left-hand side of the equation is 373.4 equals 0 minus 5 is minus 5. And then minus W electric plus 149.24. I think this one, I'm not going to round it off first. It's going to be 373.36 for the delta U. So I think it's pretty obvious to solve this problem. We just need to bring everything on the right to the left, right? So how much is it? How many kilojoules is the electrical work, or you know, the electricity supplied to the system. Okay, the electrical work to the system is, let me just give you the answer here because it's pretty much straightforward. 527.6 kilojoules. All right, hopefully everyone got this one. So this will be the solution to question 3. So that's that, 1, 2, and 3. There is 5, 7, 11, and 12. I don't think I am able to cover everything. I have only 20 minutes left. I think I want to cover this question, yeah? Example 4.6. This would be the last one for today, because this example that was supposed to be covered in class, I just didn't get the time to cover it. So I think it's a good one to cover in, let's say in our tutorial here. I'm gonna transfer this to here. Okay, so a piston cylinder system containing air, okay, 0.697 kilograms at 150 kilopascals and 27 degrees centigrade. Okay, so let's draw as always. Piston cylinder system. Okay. At this state, the piston is placed on a stopper. Okay. Stopper. And the cylinder volume is 400 liters, right? So let me just switch colors. Okay, volume is 400 liters. So that means it's 400 divided by 1,000, which is 0.4 cubic meters. Okay. I think I still love pink, right? Pink. Or purple, for that matter. Okay, 0.4. Okay. So this is state 1. All right, in order to move the piston, the pressure of 300 kilopascal is required. So now it is at 150 kilopascals. So P1 is 150 kilopascals. But then you have, hold up. This is 27 degrees Celsius. Okay. Moving to state 2, you have this thing, okay, still in the same situation, okay, except that it is about to move, okay. Let's say 400 liters, okay, but at state 2, it is about to move, state 2. Okay, so this one, T2 and T2 is now different, I think. All right, so here, piston is about to move, but this is the condition where the pressure is applied 350 kilopascals, okay? In order to move the piston, the pressure of 350 kilopascal is required. So the objective here is to move the piston. Okay, so pressure is applied 350 kilopascals. All right. Air is then being heated to double the volume. Okay. So the volume is doubled. If I may just draw it once again. Volume is doubled. Like that. Okay, so now the volume is 0.8 cubic meters. All right. So pressure is still 350. Why? Because with this pressure, yeah, the piston keeps on moving. So let's draw the boundary real quick here. That. Okay, and now the boundary has moved to become bigger like that. Okay. And the question asks, what is the temperature at the final state and the work done by air and the total energy supplied to the air. There are three things. Temperature at the final state, what is T3? Then we have work done by air. So what is the work? And we have the question asking us total energy supplied to the air in the cylinder. Okay. So energy was supplied at state, which state? Yeah. At state 2 to 3. Yeah. So energy is supplied here. So what is Q? Yeah. So this is how you dissect the problem. Yeah. You draw first. Yeah. Figure out what is going on, whether the volume is expanding, the boundary is enlarging, is it shrinking, is heat being added, is heat being dissipated, lost to the surroundings. Yeah. So draw everything first. Put down all the information. Okay. So this is air we are dealing with. Okay. Air. Our system comprises of air. Why do I always get very mild colors? Pink. All right. Air. Better. So when we say air, we can use ideal gas law, right? Ideal gas law. Now we can use P1V1 equals MRT1. P2V2 equals MRV2. And P3V3 equals MRT3. So M and R is a constant, right? Mass is always the same in a closed system. R is also a constant. So we can say that P1V1 over T1 is M times R. Same goes to P2V2. This is a typo. It's not supposed to be V2. That's supposed to be T2. So we're going to divide by T2. And finally, we divide by T3. That's going to equals to MR. All right. So then we have P1V1 over T1 equals P2V2 over T2 equals P3V3 over T3. Okay, because why? Because everything is equals to MR, okay, M times R. So we can say that P1V1 over T1 equals to this guy in the second state and this guy in the third state, all right? Any questions? This one is pretty simple, yeah, straightforward. You have seen this before. Now let me just plug in all the values, right? So we have 150 kilopascals times 0.4 cubic meters over 27 plus 273 is 300, right? Over 300 equals 350 times 0.3 over T2 is not known equals T3 is 350 times double the volume, which is 0.8. I think I had it wrong in the second one. This is 0.4, yeah? Over T3, okay? So you can now find out what is T3, right? And also T2. The question asks for T3, but let's solve for both T2 and T3. So can someone tell me what is the value of T2? Before I just pick up someone in random. Yao Yiting, can you solve for Can you solve for T2 or T3? Or even better,
T2
both?
is equal to 600.
600?
Yeah.
Is it not 700? How about T3?
Oh, sorry, doctor, is 700.
Yeah, 700, yeah? And T3 is just double. Because you have double the volume. Okay? Thank you, Yao Yiting. All right. So you have T2 and T3. Great. Now there are two processes, right? From 1 to 2 and from 2 to 3, right? I forgot to write it down. State 3. Now let's write the first law, okay? First law. We want to solve for W and Q, right? So we cannot simply use the ideal gas. We have to jump into the first law, okay? So first law says, okay, first law is from process 1 to 2 and process 2 to 3, right? So for process 1 to 2, it's U2 minus U1, right? Okay. And then you will also add up the internal energy from 2 to 3. Okay. So that's going to be, if it's from 1 to 2, you do U2 minus U1. Then if it's from 2 to 3, you do U3 minus U2, right? Okay. So this is for process 1 to 2. This is for process 2 to 3. Okay. And then you will equate this to the heat, right? From process 1 to 3. Okay. This is what we are looking after, minus the work from 1 to 3. Okay. So what do we have here? We can simplify things, right? So U2 minus U2. Can you see it? U2 minus U2. Okay, it's cancelled out. What's left is U sub 3 minus U sub 1. You see? U sub 3 minus U sub 1. Okay? Internal energy at 3 minus internal energy at 1. That equals Q13 minus work from 1 to 3. Okay. Can we let's say, can we find internal energy? It's very simple, right? It's, again, for ideal gas, it's equals to M times CV times T2 minus T1 and so on. Okay, so this one is our CV right there. So if you want to have U3 minus U1, then you have to multiply M with, okay, so U3 minus U1 equals M CV T. What's going to be for T? What's going to be for T? T what minus T what? T2 minus T1, T3 minus T1, T3 minus T2. What do you think? Okay, so because previously we saw that U2 minus U1 equals MCV T2 minus T1. This subscript corresponds to the state that we are looking at. Okay, so in this case, we are having T3 minus T1. Okay, because we are looking at state 1 and state 3. Okay, U3 minus U1. Okay, so what we have here is M times CV times T3 minus T1. Okay, equals Q13 minus W13. So this is the equation that we are going to process, okay? I'm going to delete that. And that. Okay, now what is the work, right? Work is basically the boundary work, okay? There's no other work. There's no electrical work. You know, there's no other mechanical work, spring work, whatever. We are only left with boundary work, okay? Whereby the boundary pushes the piston upward, as you can see from the figure there. So with boundary work, let me just clarify this to you. Okay, so this, let's work this out. So W13. So the work from 1 to 3 is actually a combination of work from 1 to 2 and work from 2 to 3. But do you think from 1 to 2 there is work going on? No, right? Because the boundary stays the same, you see? The boundary is the same. There's no work done by the boundary. And so you can say that this is 0. So now you are only left with work from 2 to 3. Yeah? So you will multiply, okay, work is P times final volume minus initial volume, V3 minus V2. Okay, we are only considering this guy. Okay, what is the pressure there? The pressure is 350 kilopascals, right? 350 and 350 is a constant pressure process from 2 to 3. So it's 350 kilopascals times 0.8 minus 0.4 cubic meters. Okay, that's gonna turn out to be 140 kilopascals cubic meter, which is actually kilojoules. Last but not least, yeah, let's plug in everything. So we have, do we have the mass? The mass is, have we find out the mass, or is it given in the question? Oh, it's given, right? 0.697. Okay, great. So we plug in everything, 0.697 kilogram times CV, which is 0.718 kilojoules per kilogram Kelvin, times, what's the temperature difference? So it's 1400 minus, so it's T3 minus T1. T3 is 1400 and T1 is 27. No, it's 27 plus 273, which is 300 Kelvin. Okay. So 1400 minus 300 Kelvin equals Q13 minus 140 kilojoules. Okay. So if you work this out, this will turn out to be 690.49 kilojoules. I'm going to give out the answer because you don't have too much time left. It's already 6:01, sorry, 6:02. Okay, this is the answer for this question. All right, any questions? Okay, so let me just finish this off with a PV diagram. Okay, so it's very easy to draw the PV diagram. This is a PV diagram for an ideal gas. So P and V. So ideal gas, it's like that. Okay, the graph is like that. Okay, it's a reciprocal graph. Okay, graph of 1/x. So it goes that way. And then you have pressure at 1 is 100. This is 1. The temperature is going up, is increasing in temperature. So you have temperature 1, which is 300 K for this line. And then 700 K for this line and 1400 K for this line. Okay. And then let me just change colors. I have at 300 K, the first pressure is 150. This is in kilopascals. This is state 1. And then I jump to 350 at a constant volume. There you go. Constant volume. Volume doesn't change, so it's a vertical line. This goes up to 350. State 2. And then the volume changes, but the pressure doesn't. So it goes in a straight line horizontally. This is state 3. Okay. So this, you can imagine, is the lower volume, and this one is the higher volume. Okay. Volume is in cubic meter. All right.